is there's something I forgot to talk about way back when we were talking about additivity of domain. So I should do that quickly now. So recall that the integral from a to b of f plus the integral from b to c of f is equal to the integral of a to c of f, right? So we know that's true. There's nothing crazy there. And in fact, intuitively, it should be true because, it's just saying if you add up the areas, then that's the same thing as just like, let me say this a different way. If you want to compute the area from A to C, that's the same thing as computing the area from A to B and adding it to the area from B to C. And intuitively, that should be correct. Now, one of the things that we're going to have to do in the coming week or so is talk about how does it make sense if we actually are allowed to flip which number is on top and which number is on bottom. Now, strictly speaking, integrals don't care about the orientation of your interval, right? So while integrals do not care about the orientation of an interval, we'd like to basically extend the definition to be able to account for this generalization so that we can do this, right? We want to extend the definition to account for this. Okay, maybe, no, you proved that result. So I'm not going to reprove that result. What I'm showing you here, for example, is I want to be able to make sense of this statement. Right? So where I'm sort of like my lower bound of integration is 2 and the upper bound of integration is 0. Now, again, for us, this doesn't matter, right? Using the definition of the Darboux sum, you would just integrate this on the interval 0, 2, and you don't care about flipping those two things. But there is going to be a very real sense in which, for convenience sake, we do want to be able to think about what this means and how to be able to do this. So the key to figuring out what this should be lies entirely in additivity of domain, right? So we note, first of all, note that the integral from a to a of f should just be equal to 0, right? Because this, if we take the area under the graph from a to a, there's no area, right? It's just a single point. So basically you might get a length, but you don't get an area, right? So the area under the curve is 0. So what that should say then, if we demand that additivity of domain must still be true, then if I flip the bounds, that should be equal to this thing, right? So basically what we're saying is if the orientation of the domain does matter, then when I integrate from A to B and then integrate from B back to A, nothing should happen. And I just get 0. Okay. And then if we could, we can solve now for that second term. And that tells us that if we're going to flip those bounds, then we can do that just by introducing a minus sign to the non-flipped bounds. Okay. Now, again, strictly speaking, this is a different notion of integration, right? We are extending the idea of integrability. Integrability does not care. It only cares about what the domain is. It doesn't care about whether you're integrating from left to right or from right to left. So when we do this, when we write this down, we are saying, okay, we do actually care about that now. And we're adding a notion of orientation. Am I moving to the right? Am I moving to the left into the integral? Okay. So it's technically speaking, it's a little bit different. Just kind of keep that in mind. As a general rule, we are going to use this going forward on the rare occasions where it's necessary. Yeah. Okay. Like I said, it actually will just make a couple of theorems much easier to prove. So just keep that in mind. All right. Any questions about that? Does that make sense? You probably, especially those of you who have seen integration before, you probably just knew that that was kind of baked in, but it is actually a different notion of integration. Not actually what? Okay, cool. All right, sweet. So today we are going to talk about the most important theorem. So this is the fundamental theorem of calculus. Okay, and should you so choose, you can 100% just call this the FTC. And literally everybody knows what that means, right? Because nobody wants to say fundamental theorem of calculus. So if you say the FTC, people know what you're talking about. Okay, so the FTC goes as follows. Now, if you go and you pull up a book like Stewart or something, they'll state the FTC wrong. And the reason for that is they don't go into sufficient rigor to be able to state it correctly. So your statement of the FTC is actually the right one. So suppose that I give you an integrable function. Okay, now there are two parts to the FTC. Some people call them FTC1 and FTC2. There is in no way a universal agreement about which one is FTC1 and which one is FTC2. I'm going to tell you right now, though, my way is the right way. And I'm going to explain to you why. So the function from AB to R defined by f of t dt is continuous, are what equivalent? Maybe let me state this slightly differently. So moreover, no, they're not equivalent in the sense that they don't imply each other. They're just two, but they are two sides of the same coin. So I'll try and make that a little bit clearer in a second. So let me get them down and I'll show you that they're basically this, they're trying to say the same thing, but from different perspectives. So moreover, capital F is differentiable. Wherever little f is continuous. And when so, no, that's a weird way of saying that. And in that case, f prime is equal to f. Okay, so stare at that for a second. T is just a dummy variable. So like basically, this function here, let me write this in a slightly different way. Or not in a different way. This variable here depends on x, and I want that x to only be in that numerator there. So I'm giving this a dummy. Actually, yeah, if you want, we could just get rid of that and we could just do this. Maybe this will help. Okay, so if you want to completely get rid of the t, you don't need it. The t was just a dummy variable using that notation. So, but here we do need the bounds because I am saying that I actually only want to integrate from a to this right endpoint x. Right, and actually here, let me maybe draw the function f of x for you. All right, so that's A, that's B, and maybe here's X. And so what this function capital F does is it computes all the area from A to X, right? So what I want you to do is think about moving X as like a slider, and you compute the area from A to X, right? So I wish I could, make a movie of this for you, but as I move the interval X, this shaded area moves with it. And that's what the function capital F is doing, right? Capital F is computing the area. And it turns out that function, the function which computes the area from A to X is an antiderivative. That's basically what, fundamental FTC1 here is saying. Yeah, X should be an AB just because it has to be, right? The domain of bit capital F is the interval AB. So implicitly, when I write down what X is, it has to be in that interval. Okay, so FTC1 says two things. First of all, no matter what F is, little f, if little f is integrable, big F is continuous, period. Okay, but it says something else, and something which is more important. Well, equally important. The second thing it says is that if wherever little f is continuous, capital F is an antiderivative of it. Okay, so the derivative of capital F is little f, wherever that makes sense. Okay, so this is the kind of important part of FTC1. So the statement for FTC2 is the flip side of this. So FTC1 says if you start with a function and you compute this function capital F, that's an antiderivative. What FTC2 says is going to be the opposite. It's going to say, suppose that you know that you have an antiderivative, then you can actually compute the integral using an antiderivative. So suppose that capital F is an antiderivative. Let's say continuous. Of little f, which is differentiable at all but finitely many points. Okay, then in this case, the English is not great here because I'm going to start a sentence with then. Do I need to include anything else here? I don't think so. In that case, so if you give me a continuous antiderivative, which is differentiable at all but finitely many points, then the integral is equal to the difference in the endpoint. So all you have to do is evaluate the antiderivative at the endpoints and take their difference, and that is the value of the integral. Really speaking, this is the more important of these two, because if you think about what it does, it's telling you precisely how to compute integrals. And remember, integrals are hard, right? Computing, like we saw how much work it takes even to compute x and x squared, and those are like the easiest things that we could do. Even kind of historically, when you think about, Archimedes figuring out what the formula for the volume of a sphere is, or of a circle, he was basically doing integration. Are there non-continuous antiderivatives? This is a good question. It basically comes down to usually when we do these things, again, we would take them up to measure zero sets. So implicitly here, I'm just kind of saying, I want you to make sure that the antiderivative is continuous. I will show you some pathological examples in the future where you can actually kind of get into trouble with this. The argument would probably be, well, hey, listen, if you're an antiderivative, you have to be differentiable, but in fact, we only care about differentiability up to finitely many points. So again, I'll kind of give you an example of where this can go wrong. And you'll kind of see it firsthand. Yeah. These are theorems that we could use. Absolutely, you can use these. You can use these now, right? You couldn't use them in the past. So apparently a couple students on assignment 9 or 8 or whichever one it was tried to use FTC to compute the integral of x squared, which of course you absolutely weren't allowed to do because you didn't know the FTC at the time. But yeah, you can use these now. Okay. And the interesting thing is, there's a couple of interesting points. I'll try and make these after we do the proof, but there's a couple of nice things here. So first of all, like notice in 2, we know that antiderivatives aren't unique, and it says, but it doesn't matter. You can choose any antiderivative that you want, and this will work, right? As long as it satisfies the hypotheses. And I'll show you exactly why that's true in a second. Basically, that doesn't make a difference. In number 1, you might say, well, like, does the integral have to start at A, right? When I define that function capital F, like could it have started somewhere else? And the answer is yeah, absolutely. That lower bound of integration actually doesn't make a difference whatsoever to that the statement of that theorem. And again, in some sense, that should be obvious. So I'll explain that when we get to it. Or actually, can I do it now? Yeah, maybe I could do it now. So maybe let's say the following. Let me just make sure I have all my notes. So notes. So these are notes about the results of the theorem. We'll prove them in a second. So in 1, so in FTC 1 here, the lower bound doesn't matter. Okay, and the reason for this is if C is some other point, let's say in the interval AB, and we took f hat to be the integral from C to X instead of A to X, right? Which is what the theorem currently says. Well, we know that F, which is the integral from A to X, is going to be the integral from A to C plus the integral from C to X, right? That's just additivity of domain. Which is equal to f hat plus some constant, right? That's what this is. Capital K here is just some constant. And that constant, is precisely the integral from A to C. So yeah, I mean, we know that all antiderivatives are related to each other just up to that constant, up to some constant, right? So if we'd used a different, lower point, instead of using A, like the leftmost endpoint, we had used a midpoint or just some other interval in between A, B, we would still get an antiderivative. The only difference is that it would differ from the one in the theorem statement by a constant, which we know is totally okay, right? It's still an antiderivative. So using a different point for your lower bound of integration really doesn't make any substantial difference whatsoever, right? You could have used really any point. For number 2, the choice of antiderivative doesn't matter. Right? Because if f1 is equal to f2 plus a constant, right? So I give you 2 different antiderivatives. And again, we know they have to be related to each other through a constant. So if they're just related to each other through a constant, then when I compute f1 of b minus f1 of a, right? That's the result of the theorem. It says that you can evaluate the integral using f1 of b minus f1 of a. Well, let's plug f2 into that, and you'll see what happens very quickly. Sorry, f2 a plus c. Well, the c's just cancel out. Right? So what this note actually says is, yeah, no matter what antiderivatives you use, their difference between f1 and f2, f1 of b and f1 of a is going to be f2 of b minus f2 of a for any sets of antiderivatives. So you always get the same number here. So we use 1 if we want an antiderivative and 2 when we want the area under the curve. Yeah, exactly, Adam. Yeah, that's a great way of thinking about it. So yeah, 1 gives you an antiderivative, which is nice, sometimes is very useful. Where in particular that tends to be useful is especially when you're differentiating the integral. And that does happen in real life lots of times. And then number 2 is a computational technique for actually evaluating the integral, right? But basically what this says is, in some sense, maybe we can write this as a note. The FTC says that integration and differentiation are effectively inverses of each other. It's not quite, but they're very close. Right, so the FTC says differentiation and integration are morally inverses. Okay, so they don't exactly cancel each other out, and I'll explain, maybe we'll do an example at the end which explains why they don't cancel each other out in the same way that you would expect inverses to, but that they almost cancel each other out. And the precise issue here is that constant term, right? That we know that there isn't a unique antiderivative, so they can't cancel each other out, because like if you, which is the bad direction here, if you take a function, differentiate it and then integrate it again, well, the antiderivative, the integration is effectively computing an antiderivative, but that antiderivative is only unique up to a constant. So you can't guarantee that you finished where you began, right? Because if you start with a function, differentiate it, reintegrate it again, you could get back the same function, but plus 100 or minus 70 or something, right? That constant kind of screws everything up from being a true inverse. But that's what the FTC says. It basically says that integration and differentiation are effectively inverses of one another, okay? And so this is the thing that links differentiation and integration. Historically, especially, these were just different fields, right? You would differentiate stuff, you would integrate stuff, and then the FTC is what merges them together and says, yeah, they're actually the same thing, just kind of in disguise, okay? That's why it's the fundamental theorem. So there's a lot to prove here. The proof is surprisingly not tough. It's a little bit long, but it's not tough. FTC 2 is a little bit weird. It does require a trick, but FTC 1 is surprisingly straightforward. The other thing too is, again, some people, so I don't remember whether it's Stewart or Thomas, whatever. Some books will actually, again, there's no universal agreement on which is FTC 1 and which is FTC 2. But my order is the correct order. And the reason for this is that you need one to prove two. Okay, so you can't possibly switch these around because you can't prove FTC 2 first and hope to then, because you need FTC 1 to do it. Now, the reason why other textbooks can get away with this is they don't prove the FTC, right? And so if you don't prove it, yeah, you can present them in any order. And in fact, if you're trying to differentiate yourself, let me introduce some small cosmetic differences by putting the second FTC in the first thing. So that's kind of annoying. But you need, like I said, you need FTC 1 to prove FTC 2. So that has to be FTC 1, okay? In practice though, don't worry about calling it FTC 1. F of A is equal to 0, yeah. Why, are you worried about that? Does that come up somewhere? In practice, don't separate them into FTC 1 and FTC 2. Just call them the FTC, right? Both of these things combined are just the fundamental theorem of calculus. So anywhere you want to cite FTC, just say by the FTC. But yeah, exactly, Simon, like f of A is equal to 0 for sure. But, and kind of why did you need to write it then? Where? Oh, no. Yeah, you don't know f of A is equal to 0 in FTC 2, right? Like, what if the antiderivative I used is like this one? Right from above. So it's true, if that antiderivative happens to be the one that starts at A, then that's fine, right? But again, I can add any constant to my antiderivative and actually upshift it. So this f of A does not have to be 0. Yeah, the capital F in FTC 1 has to be 0, but this one doesn't. Right? Because like we said, take any antiderivative and add 10 to it, right? And now that's not going to be 0 anymore. I can make f of A any number that I want. And we'll do an example. We'll do an example with a bunch of different, right? Like, what was it, on last Thursday? We did that example where we came up with 3 different antiderivatives. We'll do that example using the FTC, and I will show you that the values of f and b and f of A could vary dramatically, but at the end of the day, you always get the same result. All right, but let's do the proof. Okay, proof's a little bit long, I'm not going to lie, I would be surprised if I finish the proof today, but we'll see. All right, FTC1. All right, so I'm going to say fix some x in AB. Okay, and let's show capital F is continuous at x. Ooh, you know what? I'm still zoomed out, so let's show that capital F is continuous at x, right? Because that was the first thing in FTC1. It says capital F is continuous at x, okay? So for any other y, for any y in AB, including x itself, we have f of y is the integral from a to y, which I can write as the integral from a to x. No, that's going to be weird. So what are my points? Yeah, a to x f plus the integral from x to y f, right? Which is f of x plus the integral from x to y of f. So here's where, when I was talking about earlier about switching the order of the bounds of integration, you notice here I haven't said that y has to be bigger than x, even though I've kind of acted like it is. The reason I did that before talking about FTC is precisely so I don't have to say let y be bigger x and then do a separate case where y is less than x. By having that notation kind of included, I'm able to account for both of these things simultaneously. Okay, so that's just the idea there. And the great part about that is that that means that f of y minus f of x is the integral from x to y f. Right? And again, that's intuitive, especially if you think about y being bigger than x, because if you integrate from y, like from a to y, and then you subtract the integral from a to x, what is that? That's just the integral from x to y, right? Okay, so now let's let m be the soup. So that f of y minus f of x, again, I'm just going to repeat this. Now, f is always less than or equal. Is that FTC2? Is what FTC2? I mean, we're proving FTC1 here, so I haven't done anything. You mean, is this FTC2? Oh, yeah, it's kind of interesting that it does actually show up that way, right? Even though that's not what I'm using. It's not FTC2 yet. It's just me like rearranging this equation, right? The important thing about FTC2 is that works for any continuous antiderivative. So this here works for x and y. It doesn't necessarily work for, I guess I could let a and b be x be a and y be b. So it does look like FTC2, but the important thing about FTC2 is it works for any antiderivative, and this is a particular one, right? But it does look like it. So that's actually a nice observation there. Okay, so f of y minus f of x. And I mean, we haven't proven that big F is an antiderivative yet, right? So in some sense here, without looking at FTC2, we're cheating because the function capital F is defined in terms of the integral, right? So I mean, the fact that this is true is not necessarily profound because capital F is defined in terms of the integral, right? And we don't yet know that it's an antiderivative. Okay, so now if I use this, so this is going to be less than or equal to m times the integral from x to y of just the constant function. And hopefully I don't need to convince you that the constant function evaluates to that. right? And if you're not certain about that, just literally draw a picture. The function, like the integral of 1 is just a rectangle, right? And if you haven't proven this using upper and lower sums, just do it at some point. It's very straightforward. Both the upper and lower sums are exactly equal to each other. So it's very, very easy. Okay, so thus, when I take absolute values of everything, I probably don't need to use absolute values here, but. And so by squeeze theorem, the limit as y approaches x, y minus f of x is equal to 0, which in turn implies that the limit as y approaches x, f of y equals f of x. And that's what we wanted to show, right? F is continuous. Okay, so that's the first part of FTC1. We still need to prove it's an antiderivative. Are there any questions about that? Everyone's good? And you don't have to use the squeeze theorem here if you want. You could directly epsilon delta it, right? Say let epsilon greater than let epsilon be greater than 0, and then here's you're going to let your delta here be epsilon over m. And so if you want to prove it directly using epsilon delta, you can. I think this is a nice little application of the squeeze theorem, but like I said, you could just do it directly if you want. Okay, so now we need to prove antiderivative. So let's show, so suppose now that little f is continuous at x, and let's show that f prime of x is equal to little f of x, right? So when I say this implicitly too, we have to show that capital F is differentiable. But if we can show that the derivative of capital F is equal to little f, then we're done, right? Because that would be that the derivative exists, and that's what it means to be differentiable. So to do this, we are actually going to epsilon delta this, okay? And no, we very rarely epsilon delta differentiability, but we're going to epsilon delta this. So let epsilon greater than 0 be given. And suppose h is greater than 0. So to do this one unfortunately is going to be much easier if I do the one-sided limits. So I'm going to start by showing that the limit as h approaches 0 from the right. So what I'm trying to do here is I'm going to show that the limit as h approaches 0 from the right, f of x plus h minus f of x divided by h is f of x, right? Okay, just so you see what I'm doing, that's what I'm going to do. But we're going to do that epsilon delta. So yeah, so I'm going to have like the absolute value of the difference quotient in capital F minus little f, and I'm going to manipulate that thing, okay? So since f little f is continuous at x, let delta be such that y minus x less than delta implies that f of y minus f of x is less than epsilon, right? So we're saying choose the delta that works for continuity of little f at x. And now let's play around with this difference quotient. So we're going to have f of x plus h minus f of x divided by h minus little f of x. That's going to be 1 over h times the integral from x to x plus h of little f. Okay, now here I do actually need to use this notation. Otherwise, this is going to get too messy. Okay, so I've written that down. Somebody yell if you don't quite see where that comes from, but I am still just using this right here. So let me try and highlight this in green. So I'm still just using this. Okay, so it's the green box, but now y is equal to x plus h, right? So if I let y be equal to x plus h, that gives me this thing right here, right? This is the f of x plus h minus f of x. Does everyone see that? And then I divide that by h. So that's the same thing as multiplying by 1 over h. Is everyone good there? Right? Hopefully I didn't do anything which is too freaky. Okay, cool. All right, second kind of freaky thing. Basically, I want to take f of x and put it inside the integral. Okay, and it turns out you can just do that, but you have to convince yourself why. So here, I'm going to do it, and then we're going to think about why it's true. Okay, so what I want you to do, right? We know that the integral is additive, right? So what I want you to do is think about what the integral of f of x dt is. So f of x is just a constant, right? So when I integrate, here, maybe let me kind of do this on the side here. If I integrate from x to x plus h, f of x dt, right? I'm integrating with respect to the t variable here. That's going to be f of x times x plus h minus x, which is f of x times h, right? And this thing here is dividing by h. So yeah, if I do 1 over h in front, I just get f of x out. Is everyone okay with that? Like why I was able to just put that inside of the integral? Like it just worked out perfectly. Usually this step bugs some people, so don't hesitate to let me know if it does. Yes, a bit, as in yes, it's bugging you. Okay, yeah, so let's remember, x is just a constant in this integral, right? So let's just say I've got 1 over h times the integral from x to x plus h, f of t. So I'm going to split this integral up like this. Oops, I need my dt. Right, so that is that integral, but I split it up, right? Because I know I can do that, right? We know that the integral is additive. Now, this thing here, f of x, this is constant in t, right? So I can actually just take it out. So I get that first thing still just hanging around, x to x plus h, f of t dt, minus f of x over h times the integral from x to x plus h times 1 dt, right? So I just took the f of x, right. Okay, yeah, exactly, right? We have to remember what is the variable here and what's not. And then the integral of 1 is just h on this interval, and that's just going to give us the thing that we started with. So this one's a little bit weird because, again, it's kind of hard to justify this by going backwards. But like once you know what the right answer is, going forwards isn't too bad. Okay. Everyone else good too? Okay, cool. So now notice that this thing here is, up to using t now instead of y. That is f of y minus f of x, right? Except that we've just used some sort of different dummy variable. So if t minus x is less than delta, then we are going to have Actually, here, what do I want to say here? Choose. Yeah. So, yeah, how do I want to say this exactly? So choose the absolute value of h to be less than delta. So that if t is in x to x plus h, then t minus x is less than delta. Right? Okay. And so the absolute value, f of x plus h minus f of x divided by h minus little f of x is going to be equal to this thing, but let me just, hopefully this doesn't bug anyone. Okay, so I put the less than sign here, but I did that because I took the absolute value inside the integral, right? So one of the properties of the integral we have is that the integral of, or sorry, the absolute value of the integral is less than or equal to the integral of the absolute value. So I've just directly applied that. I did skip that kind of intermediate step here. Again, somebody, yell out if that bothers you. Now we know that this thing here is less than epsilon, right? So we're going to get less than or equal to epsilon over h, x to x plus h, or actually I guess strictly less than, of 1 dt. That integral is just h, and that gives me epsilon. Okay, and then I'm not going to do it, but the exact same proof holds for the when h is less than 0, right? And so the limit as h approaches 0 from the left, I guess here I should say suppose 0 is less than h is less than delta, but the limit as h approaches 0 from the left is the same. Right? It's just you always assume that h is now to the left of x. And so you'd kind of do your manipulation there. You'd have like x plus h in the lower bound of integration and x in the upper bound. But then other than that, the proof is identical. Okay, so are there any questions about that one? That concludes FTC 1. So let me zoom out, give you all of FTC 1. There's FTC 1. The less than or equal to part, sure. So here what I'm using is right? So we know that's true, right? That's one of the identities, like when we were talking about all the things that integrals can do, right? That was one of them. I think we called this subnormality. And so from this line to this line, I just plugged in this, but took the absolute value inside, right? So if you want to do it as another intermediate step, you can write, the absolute value like this, and then take the absolute value inside, but at the cost of the less than or equal to part. Yeah. Okay, anyone else? That's good. I'm not certain. Is f of y? It's not equal to f of y. It's getting arbitrarily close to f of y, right? Like, look at what So if we skip kind of the intermediate work and we look at this, and the fact that we've proven that's less than epsilon, right, says that difference quotient of capital F of x plus h minus capital F of x divided by h can get arbitrarily close to little f of x, right? In the typical sort of like limit nomenclature of they're not equal, but yeah, they get close. And that's what we wanted to prove, right? How did I use t minus x? Okay, sure. So the fact that t minus x being less than delta, remember, this implies that the absolute value of t minus the absolute value of f of x is less than delta. This comes from the continuity condition, right? That comes from so by knowing that t minus x is less than delta, it tells me f of t minus f of x is less than epsilon. Yep, thank you. And then I plug that into there, right? Because the t, yeah, if you look at the integral, right, it says I'm integrating between x and x plus h. So that t value there is always between x and x plus h, right? And that's why we're able to use that. Okay. Everyone good? So there's a little bit of stuff there. I think that this is one of the things that, again, this one's a little bit tricky to read someone else do, especially since as much as I'm trying to tell you what I'm trying to work on and what I'm trying to accomplish ahead of time, it's one of those things that I think you kind of have to see the whole proof first and then look at, kind of go back and take a look at it afterwards and be like, oh, okay, I see why we did this thing here and so on and so forth. And even then, most of this proof, even though it looks quite long, most of this proof is really just manipulating additivity of domain, right? To be able to get things like this expression, right? And that's not too hard. It just takes a little bit of algebra, right? So the majority of this proof is actually just algebraic manipulation with integrals, which is something we haven't done a lot of. But if you go back and look at it, tomorrow or something, hopefully it'll make a little bit more sense. This is actually a very intuitive proof. But like I said, it just takes a little bit of time for it to settle in for you. Now, FTC2 is not an intuitive proof. It's slick as hell, though. Super slick. It's so slick. It's really, really, really clever, okay? So what we want to show is we want to show that the value of the integral is the difference in the antiderivatives, right? And the way that we're going to do this, in fact, the way that we have to do this using our definition of Darboux integrability is we need to show, well, here, let me write out the whole thing, just to remind you what we're doing. So we want to show that the integral, and I'm going to include the bounds here, just so that, we are consistent in our notation. So we want to show this is true. Okay, how do we do this, right? What's the definition for us? i.e., we want to show that for every partition, that this f of b minus f of a lies between the upper and lower sums. Right? We've already assumed that f is integrable. So we know there is a unique number between these, between the upper and lower sum for any partition. What we want to show is that number is f of b minus f of a. And if we can do that, then boom, we're done. That is the value of the integral, right? So that's our goal. That's what it is that we want to prove. Now, the way that we're going to do this is, like I said, it's super, super slick. So we've assumed that, so let f be a continuous antiderivative. And we're going to need that. Okay, and then the assumption is that it fails to be differentiable at only finitely many points. So let's just enumerate those points. Continuous antiderivative that fails to be differentiable at Okay, I'm going to call them like D1 through Donkey Kong here, right? D for, discontinuous or, not differentiable, sort of thing like that. And it doesn't matter because I'm immediately going to throw these points away. So f is a continuous antiderivative that fails to be differentiable at these points. Let's pick an arbitrary partition. Let P, that almost looks like a fancy P. Let P be an arbitrary partition. And I'm going to do the typical thing. I'm going to refine P by sticking the D's in it. And let Q be P union D1 through DK. Okay, and I'm going to call D X1 through Xn. Is there, no, don't worry, like it's just like a terrible setup because we have to worry about these points of discontinuity, but after this, it's going to get really, really good, okay? So we've got these discontinuous points, choose an arbitrary partition, throw the points of discontinuity into the partition just so that if a discontinuity occur, or sorry, if a point of anti-differentiable, a point where your function fails to be differentiable happens at the endpoints of your partition. That's all that this big setup is doing. I just want to make sure that if your function fails to be differentiable at a point, that is an endpoint of a partition, right? That is my goal. Okay, so that's all we've done. Okay, now here's the slick thing. Now capital F is continuous on xi minus 1 xi, right? Because it's continuous everywhere. So it's certainly continuous if we restrict it to an interval. And it's differentiable in the open interval. What does this look like? What theorem am I about to use? I'll assume that was, yeah, exactly, MVT. So by the mean value theorem, there exists a CI in xi minus 1 xi such that that's true, right? But, and here's where, no, I guess actually, no, I haven't used it yet, have I? Anyway, capital F is an antiderivative, right? So that's true. And what you should see here, you probably can't see it yet, but here's where the super slick thing happens. What happens now if I sum over all the i's? I equals 1 to n, right? So if I sum from I equals 1 to n, the left-hand side is a telescoping series. Everyone agree with that? Right? Just hopefully if you write out the first couple of terms, you see, yeah, it's just a telescoping series. Alternatively, again, you can think about it in terms of sort of the picture of FTC1. Again, we're not necessarily in the FTC1 regime, but if you think about it in terms of the FTC1, I'm just saying compute the integral, like the area on the subinterval, and then I'm going to add up the areas on each of those subintervals. And what should that give me? It should give me the area on the entire thing, right? That's basically what I'm doing in this step. And now if I carry through with the MVT here, I get this. And that's not quite the upper or lower Darboux sum, but it doesn't need to be. Because I know that the upper sum is definitely bigger. The sup is definitely bigger than this, right? Because that's just some point in the interval. So the sup of the function in that interval is bigger, and the inf is less. And now I'm done. So UFP is greater than UFQ, which is the sum from I equals 1 to n. I'm going to write out the upper sum explicitly and then shortcut the lower sum. This is right. This is the sup of f of x. And the sup is bigger than the value of the, greater than or equal to the value of the function at any point inside of it. Right. Right? Because the f of c's are in that interval somewhere. And so the upper sum is definitely bigger than it. And by exactly the same reasoning, the lower sum is also lower than it. Right? And so we're done. Are there any, like, does everyone see the slickness? Right? Try and highlight with this, see if it works. Right? That thing is always between the inf and the sup. And that's how we get the result. Yeah, right? Because look at where the CIs live. Right? They live in that interval. So they definitely, like, the infimum of the function on that interval is going to be less than whatever f of ci is. And the supremum of the function on that interval is going to be greater than or whatever f of ci is, right? Or greater than or equal to. And so f of b minus f of a is always some number in between there. And in fact, you might say, okay, well, this is an exact number, right? Which is a little bit weird because, like, you know, as my partition changes, how could this still be true? But as you let your partition have more and more points, continuing to apply this theorem means the CIs themselves also become, like, the CIs have to change, right? The C's here depend on your partition because they have to live between xi minus 1 and xi. As you change your partition and as you add more and more points, this result is still true, but it has to, the way you write it down as a sum has to change because you have to start taking the CIs to be between different intervals, right? As you refine your partition more and more and more. And that's how f of b minus f of a continues to stay between the upper and the lower sums, even as you refine your partition. It never, you know, the weird thing here is the CIs change to keep you being exact, right? But regardless, you always live between the upper and lower Darboux sums. And so you have to be the integral, right? That's what you are. So like I said, two is not intuitively obvious. Two, there might be, I feel like there's a geometric thing here, but I haven't just reasoned it through. I have to draw some pictures and see if I can come up with it. But on the other hand, it's a really slick algebraic trick, right? Of writing something as a telescoping series, knowing what you want it to be, and doing that computation that way. Yeah, ends up being a really, really sort of slick argument. Okay. So here, let me get FTC2 in the whole picture. So it's a much shorter proof, but like I said, it's a little bit less intuitive. One is longer, but I think more reasonable. It's sort of the natural thing you would do. Two is shorter, but it's a lot trickier. Yeah, it's sort of like this conservation of thing. Right, I need Q precisely because I need this statement to be true. Right? So in order to apply the mean value theorem, I need that my function is differentiable. Yeah, exactly. So I need that my function is differentiable on the open interval of the partition, right? Which means if my like where I fail to be differentiable has to be at the endpoints. So I have to make sure that I refine my partition so that the points where I fail to be differentiable occur at the endpoints of the partition. Now, if you wanted to, you could skip this and you could say, no, really, you should do it this way because you want to show that this is true for an arbitrary partition. And so you can refine it after the fact. But the fact that we want to use the MVT means that the points where we fail to be differentiable have to be at the endpoints. Yeah, exactly. Exactly. Right. So I think that's a pretty slick proof, all things considered. It's a really nice application of the mean value theorem as well. Really, really nice application. Okay, and I've kind of mentioned it to you before that the mean value theorem is a sort of Rosetta Stone between differential information and non-differential information. And here we're kind of using it backwards. But if you look at the statement of FTC2, that's more or less exactly what's happening. You know, up here, you've got this statement that's relating the integral of a function with its antiderivative. There's again this interplay between differential and discrete information, right? The stuff over on the right-hand side, this is discrete stuff, right? And this stuff is like infinitesimal stuff. So the mean value theorem here is playing that same sort of role of translating between infinitesimal and discrete information, as it always does, right? And that again, like you might not have guessed FTC comes into it, the mean value theorem comes into it at this point. But if you again remember that the mean value theorem plays that role, you can predict it after the fact. Hindsight's definitely 20/20 here, but it does help out. Okay. All right, now's probably a good time for us to take a break. I think we're all probably like proofed out as we spent, the better part of an hour proving the FTC. And let's just look at our body of work in its totality. Look at that. Let's try and get the whole proof in. Hopefully it's readable. Just pinch a bit more. There we go. Basically, there's our proof of FTC, right? All right, let's take 10. We'll come back. I'll do a couple of examples of the FTC so you can really see it at work. And then, yeah, I think that'll probably take up the majority of the lecture. So I have 10:13 by my watch. We'll come back at 10:23 and we'll finish it. We'll do some examples. Okay, and again, you can throw questions in the chat. I'm happy to answer them. I don't know if you can read that proof because it's a little bit stretched out, but there's the whole thing for you so you can look it over. All right, see you in 10. All righty, let's get back. Let's do some examples. Should find a way to change my highlighter color. Oh, it looks good on green. I don't know. I'll have to think about it. Okay. So a couple of examples that we can do. Let's maybe even cover some things that we've talked about before, just to cement some things in the reality of what we've computed. As a first example, an obvious thing might be the integral of x squared, because you had to do that on an assignment, right? So find the integral from a to b of x squared dx. So according to FTC2, in order to do this, the only thing that we need to do is find a continuous antiderivative, right? Which is almost everywhere differentiable. And to do that, I think there's a natural candidate. It's 1/3 x cubed, right? So capital F of x 1/3 x cubed is an antiderivative So by the FTC. And I'm doing this just because this is, our first couple of examples after doing the FTC. You don't have to say by the FTC. You can just start computing. X squared dx, that's going to be f of b minus f of a, 1/3 b cubed minus 1/3 a cubed. And yep, that is exactly what we found on the assignment, right? Only way easier now, way, way easier. So that's nice. Let's do another example. So I mentioned that we had this one from Thursday. So let's find the integral from 0 to pi by 2 sine, let's use theta. Just to emphasize that the variable doesn't matter. Sine theta, cos theta. The reason I want to do this one is on Thursday, we found that, there were like we could find 3 different antiderivatives of this thing pretty easily that didn't just look like one another up to a constant, even though we knew they were. So we know, so I'm going to call them F1. It's 1/2 sine squared. Oh, sorry, maybe let's call them in terms of theta. Sine squared theta. F2 theta is -1/2 cosine squared. And then what was the last? So it was like -1/4. I think this is the other one, right? Cosine 2 theta. So we know these are all antiderivatives because we checked this, right? We checked this on Thursday. Our antiderivatives. So the integral should be just their difference between our 2 endpoints. So f1 of pi by 2 minus f1 of 0. Okay, so if we do that, f1 of 0 is 0. Sine of pi by 2 is 1, so we get 1/2 minus 0, and that's 1/2, right? Now, if we do, and again, we know the answer is 1/2. We could stop here, but what I really want to illustrate is that these might not give you 1/2 minus 0, but at the end of the day, you're always still just going to get 1/2. So if we do f2 now, so we get f2 pi by 2 minus f2 of 0. So cos of pi by 2 is 0. So this is going to give us 0 minus, and then cos of 0 is 0, so minus -1/2. So that gives us 1/2. All right. Maybe that's not surprising because we know that sine and cosine are related in this way. So let's, f3 though, I think is going to be more interesting. So f3 of 0. Okay. So cos of 2 times pi by 2 is cos of pi, which is -1, right? So we're going to get 1/4 minus -1/4. And that is also equal to 1/2, right? So you can see that no matter which of these antiderivatives I use, I get the same answer. And the evaluations themselves might end up being totally different. But at the end of the day, their differences always end up being the same number, right? So you can really use any antiderivative that you want. So that's very reassuring, right? Otherwise, we'd be in a lot of trouble. Okay, so both of these are FTC2. Let's maybe try and see something with FTC1. And this example, you don't have to do using FTC1, but all right, so suppose, let me give you a domain here. G maps, no, yeah, I chose a function where we could do R to R. So find G prime of X, right? And this is a crazy looking function, but it's totally a valid function, right? Like if I give you a number, x is equal to 2, then in order to figure out the output of g, you would compute the integral from 2 to 4 of t plus 2 over t squared plus 1 dt. Maybe let me make this clear. This is a t squared plus 1, right? And you could do that because you know t plus 2 over t squared plus 1 is continuous, therefore it's integrable, therefore that number exists. But here's the thing. I specifically chose a function which is kind of nasty to integrate. It's not impossible to integrate this function, but it's a little bit tricky. So you don't actually want to compute the integral of this function and try and work it through. Instead, what you should use is the fundamental theorem of calculus, because I've asked you to compute the derivative of an integral, right? And it seems like this is a kind of a perfect place to do that. So let's use FTC1 to help us. And then I'll show you how you can use FTC2 to do this. So what I'm going to do, the problem here is that in order to be able to differentiate the integral, which is what FTC1 tells us, the lower bound of integration has to be a constant and the upper bound of integration just has to be an x. Here I'm in trouble because the lower bound of integration is an x and the upper bound of integration is x squared, right? So we've got to reduce this into a simpler problem. So what I'm going to do is define this function. So capital F of x. And I'm just going to choose a lower point at, arbitrarily. It doesn't matter. Like so. Okay. Now by FTC1, we know what the derivative of this function is. Right? It's x plus 2 all over x squared plus 1. Okay, so that's what FTC1 tells us. Now let's rewrite g in terms of f. So g of x is the integral from x to x squared, right? I'm just going to rewrite it, t squared plus 1 dt. Let's use additivity of domain. Minus the integral from 0 to x. Oops. T plus 2, t squared plus 1 dt. And now that's f of x squared minus f of x, right? All right. And now we can differentiate it. So g prime of x is this thing, right? And we know how to differentiate everything in here. So that was the whole point of this. So 2x f prime x squared minus f prime of x. So that's going to be 2x times x squared plus 2 over x to the 4 plus 1 minus x plus 2 over x squared plus 1. I'm not going to give this a common denominator. I don't care enough. And we're pretty much done. Right? So that's how you could do that. Alternatively, what you can see here is a hint of how to use FTC2 to help us out. Right? If you look at the underlying yellow stuff, which is basically to say, so alternatively, let f be an antiderivative of, let's say, little f of x equals x plus 2 over x squared plus 1. So the integral from x to x squared of little f of t is capital F of x squared minus f of x, right? And that's exactly, right? This is exactly the yellow stuff above. So it kind of lets you get to this step for like, I don't think faster. It's basically the same amount of work, but basically you can use either FTC1 or FTC2 in order to arrive at this. Yeah, there aren't too many nice examples of using FTC1, except for when you do need to differentiate under the integral sign. But this is the sort of thing to keep in mind here. Okay. So any questions so far? Is this making sense? So this is very nice. Tells us how to differentiate integrals and how to compute integrals using antiderivatives. Okay, and now let me see. Indefinite integrals, and then this stuff. Do I want to start this stuff? So 1, 2, I could probably just do that. Well, let's see. Okay. Well, if there are no questions about that, let me just very quickly tell you about indefinite integrals. Okay, and basically the idea is that we don't have a symbol for take the antiderivative, right? We have a symbol for take the derivative. It's d over dx. Well, what do you mean by finding the antiderivative? Like next week, we're going to talk lots about how to do that. Or we don't. Okay, so yeah, I don't know what you mean by finding the antiderivative, or maybe that's part of the indefinite integrals thing, but I'll explain what an indefinite integral is here. And basically the problem is we don't have a symbol for taking the antiderivative, right? So it's really annoying because I just write down a function and then I have to write down the words find an antiderivative. And then more importantly, it's not finding well, it kind of is finding the antiderivative. Yeah, it's more of just a notational thing, right? So, excuse me, we don't have a symbol for taking the antiderivative. And moreover, there's no such thing, excuse me. More importantly, there's no such thing as, well, that's just it. Yeah, so we're going to use something like that. But more importantly, there's no such thing as the antiderivative, right? There's no unique antiderivative to a function. There are, in fact, an entire set of possible antiderivatives, right? And moreover, there is no unique antiderivative. Right? Which means that whatever we do, if we, first of all, invent a symbol for taking an antiderivative, its output can't be a function because that would not be well defined, right? Because do you output, like in the above case here, let's say I said to, take an antiderivative of sine theta cos theta. Well, which of these three functions do you output? And do you output any of those plus 100 or something, some other arbitrary constant, right? So even if we invent a symbol for taking the antiderivative, it can't output a single function. It has to output, in order for it to be well defined, it has to output all of the possible antiderivatives, right? Does that make sense? So, and if not, let me know. But basically, if we're going to invent a symbol for this, its output has to be the collection of all possible antiderivatives. Okay, so to kind of fix both of these at the same time, what we're going to do is we're going to define the integral of f of x dx. Okay, so again, the important point here is there are no bounds of integration. And remember when I was first telling you about the notations that you were allowed to use, and we said that this is means the integral? That's a real number. That is different than this, right? Even though there were no bounds here, oh, maybe I'll talk about this more later. Even though there are no bounds here, right? That's a real number. That's not what we're about to define. So the integral of f of x dx is going to be the collection of capital F's such that f is an antiderivative of little f, okay? But we know that all the antiderivatives are unique up to a constant, right? But so this is shorthand, right? We have to be careful here because we're abusing notation. So these are the collections of f of x plus c, where f is some antiderivative. and c is a real number, right? And because that's a lot to write, we often cheat and just write f of x plus c like this, okay? But this is abusive notation. When we write that plus c there, and this screws up a lot of people and a lot of students all over the world who are learning integral calculus. That plus c is a shorthand for the set above, right? It's saying I'm allowing c to run through all possible constants and thereby enumerating every possible antiderivative. Okay, so when I write that, this is a set, right? This is a set. So for example, if I write this, what I want is the collection. Yeah, and so it's understood that C here belongs to the reals. And so you don't even need to include it. And that's part of why this is an abusive notation, but it's a universally accepted abusive notation. So that's okay. Right? So we might write something like this. The integral of x squared dx is 1/3 x cubed plus c. Again, we identified that the thing on the right is a set. It is an infinite set. It has the same cardinality as the real numbers, right? It's uncountably infinite. This is not a function plus a fixed constant. This is this function plus every possible constant, right? That's what we're doing when we write this down. This screws up a lot of students. Because they don't understand this idea. Students will throw in plus c's when they're computing real numbers. That doesn't make sense because you're not computing the set of antiderivatives, so don't do that. Students will forget, they'll be asked to compute an antiderivative and then we'll forget the plus c. But that's wrong as well. You need to have an infinite set. You gave me one function, right? So be aware of what the plus c means here and how to use it correctly, right? That's important. The other thing to kind of note here is we've really overloaded this integral symbol, right? So notationally now we've got a lot of different things and I want to write them down so that we can kind of see them all in the same place because we're not like, this is pretty much it. We're going to define improper integrals, so we're going to overload it again. But we've got a bunch of different notation. So the following are just numbers, right? So we said the integral of f, we said the integral from a, b of f, the integral a, b, f, the integral from a to b, f of x, dx, the integral from a on a, b, f of x, dx. Okay, these things are numbers, right? They are real numbers. The following is a function. Or we might write this as a to x f of t dt, right? Or, some possible variation of the notations above. Can we write r under the integral sign? Like you want to do like this? Like the real numbers? Yeah, no, we can't do that yet. We will one day, but not yet. And the reason for that is the definition of an integral requires that you use one of these things, right? You have to use a closed and bounded interval AB, and the real numbers are not a closed and bounded interval. So we can't do that yet. We will talk about how to do that a little bit later, but not yet. And then finally, now that we have indefinite integral, we have the following are sets. Well, actually, I guess this is the only notation we have for it. Okay, so you can see here we've used the integral sign in a lot of different ways. Contextually, it should be clear whenever we use it what we're asking for, but do take a step back and try and make sure that you don't get these confused. In particular, the places where people get upset is like I said, this is a totally well-defined notation, right? Because your function has a domain, and that domain is implicit in the datum of f, or in the data of f. So this is totally fine. However, the plebes out there who didn't take real analysis, right, think that if there's no bounds of integration on the integral sign, then it's this thing. And so if you write the top thing, you might run into problems in real life where people get upset with you because they're like, well, that's an indefinite integral. What are you like? What's the domain you're integrating it on? And they'll get really upset with you. And then you have to explain to them that, no, you took a real math class and you actually know what this means, right? But just be aware of this. This is going to happen. If, for example, if you ever go onto Reddit and write that, people will lose their minds because most people have only taken, first year baby calc and have no idea what that means. So just be aware of that. There's lots of people in the world who think they know what they're talking about and don't. Oh yeah, yes, definitely from experience. The best is, again, like the people on Reddit who have enough mathematics to think they know what they're talking about, but they don't actually have enough mathematics to know what they're talking about. Do you know what I mean? It's the sort of thing that, like, if you're a third year math student, and so not to crap on the Americans, but the American university system is generally exceptionally weak, right? Like exceptionally weak. There are obviously the Ivy League universities and the great universities like, Caltech, Stanford, et cetera, plus the Ivies. And those universities are great. And they, will teach math at a very high level. But exactly, for everyone else, they, like, the math you're doing now at the other 99% of American universities is beyond what they would learn in third year, right? This course is a third year plus course at the average American institution. So if you do something like go onto Reddit and you start talking to people about epsilon delta, first of all, they have no clue what you're talking about. You will have fourth year math students at American institutions who have not seen the epsilon delta definition of a limit. You are learning it in first year, right? So this is what I'm saying. It's very easy for people to be like, well, I'm a math major, I know what I'm talking about. And you'd be like, no, man, you don't. And exactly, yeah, which is another thing, which a lot of European universities will start doing, like group theory in high school, right? Which for us is a third year course. So, but just be aware, there are lots of people out there in the world who think they know math and they don't, right? And you have already now seen a level of analysis that puts you well ahead of, 90% of the people out there who have math degrees, right? Who have mathematics degrees. You now have a stronger analysis background after taking this first year course than most of them. So just be aware of that you are going to run into these people. You're probably okay if you're in the math subreddit, right? If you're on r/math, you'll be okay. But if you're on anything else, people have no idea what they're talking about. It's just the number of people out there, like I said, who think they know math is disturbing. And it's almost just not worth engaging in them with conversation because they just have no clue what they're talking about. Sure, even that. So and obviously there's going to be a lot of variation, right? So I'm sure that not all French schools are the same, just like not all American schools are the same. Not like same thing with Ontario. There are, different levels of high schools in Ontario, and there are some really good high schools. Most Ontario high schools are garbage. But for sure, I have a lot of colleagues who, for example, one of my German friends went to a German school for mathematics in high school, and you can imagine they were doing some very advanced stuff. Same thing with many of my Russian colleagues. In high school, they were doing some very advanced stuff. I think, though, and I don't want to speak universally, but there was a little bit more streaming that was going on there, right? Like they knew they were going to be mathematicians very, very early and were able to go to schools that were specialized for this. And that does exist to a certain extent, in Canada and the United States as well, but I think not to the same degree. One of the things that we even talk about in Canada, right? So I for example, am grossly, like I am very disturbed by the average student that we get from Ontario high schools. Like they are generally very, very weak, right? The average Ontario high school student is exceptionally a weak student. Sure, yeah, there you go. Yeah, so the average Ontario student is very, very weak. But that being said, the average Ontario student that we get is still stronger than the average American student, right? Which again, isn't an indictment of the American themselves. It's just their school system is so garbage in general, on average, that this is true, right? There are lots of, for example, textbooks, wonderfully written American textbooks that when we gather in conferences, we're like, we would love to use this because this is so brilliantly written. But the level that this book teaches at is too weak for Canadian students, right? Like the American system is so weak that their books are too weak for us to use, even though we really like the way these books are written and the way they're presented, right? So this is an unfortunate reality of this situation. And yeah, it's you get all sort of weak or interesting things. So for example, I had a student who did her education in Texas, and in Texas, she was an advanced student and she came to like Ontario in grade 10 and was just behind in everything. But then you get the flip side of this, where students who went to very strong universities strong high schools in the US and were more advanced than Ontario students. No. So the important point is the United States has some of the best schools, but on average, their schools are terrible, right? And this is, I feel like the American model in general. The Americans have some of the greatest schools in the world, right? Easily, if you take a look at the list of schools in the top 20 grad school university grad schools in the world, the United States just overwhelmingly fills that list. But you're talking about 12 schools sort of thing, right? 12 to like 15 schools in that list. But there are way more than 15 universities in the United States. And the overwhelming majority of those universities are just terrible, right? So it's the same sort of thing. The United States also has the richest people in the world, but overall, they also have some of the, like a huge number of extremely poor people, right? And so if you choose to focus your highlight just on, the richest people or the best schools, of course they look phenomenal, but on average, they're actually quite weak. And this is the sort of interesting reality of this from an education standpoint. The Americans are very, very weak. Phenomenal grads, like a couple of very exceptional schools. And then the rest of them are so unbelievably weak. So, it's this sort of sad and interesting thing. But whatever, good students find a way to thrive no matter what environment they're in. So, don't worry about that too much, but yeah, that is totally a thing. Okay, so yeah, I actually don't want to start on the next lesson that I'm going to do, which is this mysterious function that we call the logarithm. I'm going to save that for Thursday. I don't want to start that. I'd rather kind of keep that as a self-contained thing. So does anyone have any questions? Everyone's good? Sure, Adam, what's up? But linear algebra, we saw lots of exponentials in the complex field, and the teacher insisted it was just notation, not a real explanation. Last time we talked about sine cos. Okay. I mean, right. Yeah, so let me ask you the following. So let's say we're dealing with the complex numbers, and I write down e to the 2, and this is a complex exponential. Like that number agrees with the real exponential, right? Like it has to. The definition of the complex exponential is such that when you restrict to the reals, you get the same thing. So it really depends, and you're right, we were cut off last time. One of the things that I was saying at that point was, no, okay, first of all, let me ask you about this. What does it mean to exponentiate two numbers, right? Like if I write down I to the power of I, what does that mean? Right? And so obviously we have to interpret this in some way. So, and I was talking about this last class as well. What does pi to the power of e mean? Right? There's some sort of ambiguity here in the first place because we can't say take e powers of pi. That doesn't make any sense. So already we have a classical notion of exponentiation, which generalizes the notion of multiplication, right? Exponentiation is repeated multiplication. But once we even start to do things like take half powers of this, we've already said this is no longer exponentiation, right? This is just notation. Does that make sense? But nonetheless, it generalizes the exponentiation rules in a sensical and compatible way. So there is a real sense in which this, as a purely real number definition, is not actually exponentiation. It is a symbol which represents the number which, if you exponentiated it twice, would give you 2. And then that becomes even worse if we were to replace this number by pi, because we have to interpret what does that mean. And again, that's not real exponentiation at that point either. So the question I have is what do we consider to be real exponentiation? Is this real exponentiation? Is this real exponentiation? Where do we draw that line? And you could make an argument that the only exponentiation which is real is if you take a real number to the power of a positive integer. Right? And yes, if that is the only way exponentiation is actually meaningful, then yes, e to the x in the complex field is not a real exponential, but neither is e to the x in the reals. Do you know what I'm saying? So where do we draw that line? And I would say if e to the x is real exponentiation, is proper exponentiation in the reals, then e to the x is proper exponentiation in the complex numbers as well. Right? So it depends on what your interpretation. The problem here, like all problems, is that what is the definition of actual exponentials, right? What is that definition? Wait, are you saying, Tina Rand, are you saying it can or cannot be? Because why couldn't I to the I give you a real number? What's the issue with that? Right? It's okay. Like you can get real numbers from complex exponentials. There's no problem with that.
Hello.
Hey.
But like, is there any answer to this question where we draw the line, or is everyone drawing the line wherever they want?
I think the issue is that nobody is really even concerned about the line, right? Like there's this thing called e to the x, which is a function, and it behaves in a way that everyone agrees upon. It generalizes the notion of exponentiation, and like nobody's worried about what the definition of real exponentiation is. Right? It's just we all agree that this is a notion of exponentiation because it generalizes what we would do for positive integers. And if it does that, and again, we all kind of agree and accept that this is a generalization, then we would still call that exponentiation. And so I would say in the complex numbers as well, we all agree that this is now a generalization of the real exponential to the complex exponential, and therefore it's real, it's still just exponentiation, right? And there's a sense in which this continues to be abused. For example, there is a sense in which you can exponentiate matrices, right? And that is a valid form of exponentiation. There is a way in which you can exponentiate group elements to get algebra elements. And we don't really understand what that means, but I would argue that that is absolutely a legitimate form of exponentiation. All of these things just generalize a concept that came before them, which generalizes a concept which came before them, which generalizes a concept which came before them. But all of these notions are still compatible notions of exponentiation. So at the end of the day, we just say they're exponentials. And if somebody wants to define what actual exponentiation is, then we can have a conversation about that. But no, it's all still exponentiation, right? And yeah, I think what your high school teacher was saying was okay, but might have been misleading, right? In the sense that it's not just us throwing away what we think exponentiation should do and using purely notation. That's not correct. But there is a sense in which we've generalized so far from the original notion of exponentiation that it doesn't quite behave the way we would expect it to anymore. And so, but we keep a consistent notation. That's true. But I think that, something was lost in between in that description somewhere. So yeah, it's a matter of interpretation, I think.
And because of that, like, but this exists only in the complex field. Like we
Yeah,
cannot
and it's cosine plus I sine.
Yeah,
Right.
but we cannot like put it down in oh yeah, I sign. I forgot the I. Like we cannot put it down in the real field.
Yeah, sure, that's true.
Okay.
But like one of the cool and interesting things that happens is that the real numbers can still detect their complex number counterparts, even when there's no notion of complexity involved whatsoever. The purely real functions can detect issues with their complex counterparts, which is one of the coolest things that's going to happen when we start talking about Taylor series. So basically, what we're going to do is we're going to talk about something called radius of convergence. And what the radius of convergence does is basically looks for the first place where your function effectively has a vertical asymptote. You can think about it like that. So if I've got a function and I'm looking at 0 and the function looks like this, and I look at the radius of convergence, let's say this happens at the number 2. If I look at the radius of convergence of this series at 0, it's going to be 2 because it goes as big as it can until it finds an asymptote, right? A place where the function explodes. Now, the interesting thing here is that if you do this for arctan, right? And arctan looks something like this, right? If you compute the radius of convergence for arctan at 0, you get 1. And so the question is, well, okay, what the heck happened here? There are no asymptotes for arctan at plus and minus 1. So why is the radius of convergence only equal to 1? And it turns out if you plot arctan in the complex field, there's an asymptote at I, and I is at exactly a distance 1 away from 0. So this function arctan x, which is purely defined in terms of real numbers at this point, when we compute its radius of convergence, we'll be able to detect its complex asymptote. And those asymptotes are called poles. So the correct word for this is a pole, but arctan is able to detect its complex pole. And that's what restricts its radius of convergence. So there are weird things happening here where even purely real things can still detect their complex counterparts. And this is this is a really, really cool thing that ends up being true. Okay, so you kind of have to, I'll talk about that a little bit. We're obviously not going to talk about complex analysis in this course because it is actually an entirely different field. When you start talking about being able to differentiate on the complex numbers, you have to reinvent calculus. It becomes much more complicated. That's something you would see in third year if you go take a complex analysis course. We will do this for the real stuff, and I'll talk about that a little bit, but unfortunately, we won't see that. That's just something you'll have to keep in the back of your head until you go and you take a third year complex analysis course. Finding the radius of convergence, no, it does not involve any complex numbers because the radius is always going to be a real number. And because even if you're in the complex numbers, if you're measuring distances, your distances are still real, right? Because you still need, the distance between these two complex numbers, we demand that we can only prescribe real number distances between things because complex number distances are kind of weird. There might be a weird generalization of that I'm not aware of, but we usually demand that measurements are real valued. C is isomorphic to R2. So first of all, when you say C is isomorphic to R2, you have to be very precise about what it's isomorphic to as. So they're isomorphic as sets. They are isomorphic as real vector spaces, obviously not as complex vector spaces, but they're isomorphic as real vector spaces. They are isomorphic as They're isomorphic. They're not isomorphic as algebras because R2 does not have an algebra structure. They're isomorphic as metric spaces, as Euclidean metric spaces. They're isomorphic as Euclidean topological spaces. Right, so it depends on how they're isomorphic. They are not, maybe, but that ends up not being related to radii of convergence, right? So they're not related as differentiable spaces, right? As smooth spaces, as smooth manifolds. They are not related in that sense, right? The collection, so complex and real differentiation are completely different things. And the things that are true about reals are just no longer true about complex numbers, right? Like I can't remember if I've told you any of these. There are no non-constant bounded complex functions. Like if you are a differentiable function on C and you are bounded, then you have to be the constant function. Right? That's clearly not true in the real numbers. Arctan is an example. It's bounded, right? Sine and cosine are examples. They're bounded differentiable functions. In the complex numbers, if you're bounded and differentiable, you're constant. In fact, it's one of the first and easiest proofs that you do in complex analysis. I don't have there isn't a great way for me to explain it. Like basically it just works out. Once you derive the theory of holomorphic functions, this just has to be true. It's very hard to give a geometric insight for what happens here because once you start dealing with functions on the complex plane, your geometric insight kind of goes out the window. I've always actually really found complex analysis very challenging, precisely because my intuition is grounded in the reals, and so I've always really struggled with complex analysis. It's one of those things where I just basically have to shut up and compute and shut up and prove because I don't usually have enough of an intuition to make strong arguments. But there are some people who are really good at complex analysis, and those people are just, they know how to think about it. I don't, like I said, I don't actually have the insight to be able to do some of those things. Same sort of thing, like almost every complex function is totally surjective, right? So complex differentiable functions from C to C can miss at most 1 point. So if you miss 2 points, you're a constant function, right? So if you look at the range of a complex thing, it's either all of C, it's C minus exactly 1 point, or it's exactly 1 point, right? The range of a complex differentiable function is either C, C minus a point, or exactly 1 point. That's it. Those are the only ranges that a complex differentiable function can have. All right, so complex analysis is really weird. Because you can't, the moment you do, it forces you to become constant. Right? It's not possible to miss 2 points. Like if you define, and part of this is like the functions that you can think about, like things like sines and cosines. Well, yeah, so you have poles, for example, and poles basically force you to hit everything. But even sine and cosine hit everything. Sine and cosine become surjective functions in the complex numbers, right? So, which is weird when you think about it, but that's totally, it is a thing, right? Sine and cosines are not bounded anymore. So weird things begin to happen by virtue of starting to work in the complex plane. But that's something to wait until you learn complex analysis about. It's very, very weird. All sorts of crazy theorems. If a function is once differentiable, it's infinitely differentiable, right? There are no functions that are only differentiable twice or something. So if you're differentiable once, you're differentiable as infinitely many times. All differentiable functions are analytic. We don't know what that means yet. Yeah, exactly. Yeah, it's one of Picard's theorems. All differentiable functions are analytic, which means they always have a non-zero radius of convergence, which we haven't talked about yet. So yeah, all differentiable functions are analytic. You can compute integrals by looking at residues, which is one of the craziest things that's true. You don't know what that means, but basically, if you circle a pole and you compute an integral around a pole, you can use this to compute integrals in general. So this is called Cauchy's residue formula. You can wiki it if you want. It's one of the craziest theorems in complex analysis, as far as I'm concerned. And it's not terrible to prove either, but again, it's just nuts. Yeah. Is it the same way we pass from Q to R that there are things? Certainly, that is true, but we usually don't do calculus on Q, and maybe that's why we run into some of those problems. So certainly there will be things that are true about Q that are not true in R, right? If just nothing else, their cardinalities are different. Q is not like connected, right? There's always an irrational number between them. Things like this begin to, give you troubles. But if you could somehow talk about calculus on Q, which you can talk about like sequences and stuff. So if you talk about sequences on the rationals, they agree with sequences in the reals. That generalization of the rationals to the reals doesn't break a lot of things. You might get some more complicated results, but it generally doesn't break it. C is a completely different beast. Like I said, try and find a book on complex analysis, and you'll see within the first couple of pages that the definition of differentiability is completely different. Because first of all, there are two different notions of differentiability. There is holomorphic and anti-holomorphic functions. And like basically you all know about complex conjugation. In effect, when you conjugate a function, you break its differentiability. And you don't want to be able to do these sorts of things. Anyway, you have to look it up and look at like the Cauchy-Riemann conditions for integrability. But there's a notion of being holomorphic and anti-holomorphic. Holomorphic is just a fancy word for differentiable. So you can be differentiable or you can be anti-differentiable. And so there are implicitly two different notions of differentiability in the complex numbers in and of themselves. Suggested textbooks for complex analysis. So there's the classic textbook, which is Alfor's. Alfor's is probably not super accessible though. It's a fairly old book, but it is the book. It is the book that like everyone grew up on. Everyone has a copy of Alfor's on AHLFORS. I'm pretty sure it's Alfor's, but if you just look, even if you misspell it in Google, it'll probably correct you. Alfor's is the book. Other than that, though, I don't have a strong preference. And I'm not certain that Alfor's is a book you want to like self-study from. But that being said, I don't have a good one. I don't have a good recommendation for a complex analysis book. Yeah, but like I said, everyone uses Alfor's. I'm kind of split on Alfor's. Alfor's does some things well, but it is actually a really old book, Alfor's complex analysis book. And so some of his, I think, terminology is actually outdated. And so nobody uses it anymore. And you have to, as a result of that, you might not want to learn from it because there's been advances in the field since Alfor's wrote the book. Notation has changed, terminology has changed. And if you don't know how to translate between those things, it could actually lead you down a weird direction. But yeah, I think most baby complex analysis, if you want to self-study, choose something that's designed for like 334, not 354, right? Don't do the specialist version of it quite yet. Maybe just baby introduce it and then worry about trying to find a 354 thing. And like anything, find someone's notes online. Like there's lots of people who have probably, complex analysis is a standard course at most universities. There are probably hundreds, if not thousands of people who have written course notes. And those notes will be great learning resources. So if you want to see that sort of stuff, that's probably a great way of doing it as well. Okay. Anyway, we're running over here because people are apparently interested in the complex numbers, which is cool. But I think we should call it. Are there any like last minute questions? Let's see. No, everyone's good. All right. Yeah, awesome. Thanks, everyone. I will see you. Yeah, no problem. I'll see you on Thursday. Don't forget, you have a test on Thursday night / Friday. So start studying, study hard. And I will see you on Thursday morning. All right. Bye, everyone.